Good afternoon. This is the Virginia State NASA Robotics mining team. We are located in Petersburg, Virginia. Our team has worked on the project very hard this year, and we're hoping to give you guys a good presentation.
My name is Alexander Walker, and I am a computer engineering major.
My name is John Shalata, and I'm a computer engineering major.
Janton Shorter, manufacturing engineering and math double major.
Mechanical engineering major.
Hamilton Winstead, manufacturing engineering major.
Joshua Christensen, mechanical engineering and math minor.
Good afternoon again. My name is Alexander Walker, and I'm a proud member of Virginia State University Trojan Mining Crew. So Virginia State University has been a part of the NASA competition for its 4th year now, and we're glad to be back. So today we're going to be talking about our unit design for the NASA robotics competition. So today, this is kind of like the outline of what we're going to be discussing today. So we're going to go over the introduction, our safety plan, followed by our performance goals, then our design philosophy and process, and then we're going to end it off with our alternative analysis, the final product, our innovation, and our project management.
Hello, I'm Hamilton Winstead again. The NASA robotic mining competition presents a very relevant astronautical challenge for university students to solve as space agencies around the world gear up to do more long-duration manned and unmanned missions. Taking supplies to these locations, such as the moon or Mars and other astronomical bodies in the solar system, is going to require an amount of water that is inefficient to carry from Earth to space due to current launch costs and fuel efficiencies. But we found that on these astronomical bodies, the present water in the form of icy regolith has the potential to be mined to be used as fuel, drinking water, turned into oxygen, and many other things. As we know, the Martian environment is not very friendly towards human activity and of any kind, due to, and this is reflected in the rules of the competition, due to dust storms, the distance from Earth to Mars, data consumption, and dust mitigation are very important in competition, and points are given and deducted for how well teams do both, as well as the movement for our team's robot on the Black Point 1 surface is very important due to it not being like sand and it being having its own individual properties that make it difficult to maneuver on. Our design from last year had many strengths. Was a simple design, and it was a lower cost than most teams. Our robot, this simple design allowed us to be able to make changes very quickly. We used a large amount of standardized parts, and as we went on to make modifications for what we found worked and what we found didn't, was easy and simple. Our primary focus, one of our weaknesses from last year was that our primary focus was on mining, and we had not thought about the issues our robot would have traversing over this strange material. And so, although while our mining was good, when we found we had trouble and issues in working in the mining arena. Our robot from last year was actually recycled and used in a senior project showing the versatility of our robot. It was used as an autonomous spraying robot for small farms.
Of course, safety is always important at Virginia State University. 3 areas I'm going to go over really quickly are general safety guidelines, machine shop rules, and robot safety. First of all, general safety guidelines, we will always be wearing heavy gloves when picking up sharp objects, and also wearing glasses during the lab and in the shop. Of course, proper housekeeping is important in the shop to ensure that personnel do not trip over items around the shop area. Machine shop rules, certification are required by all personnel getting certified on the equipment, the lathes, the mills, and all the hand equipment by the professors. Everybody will work in buddy teams, and where if anybody gets hurt or injured, the other person can provide first aid and help the other person. Regular preventive maintenance checks and services will be done on everything from the hand tools to all the machines at the shop prior and after operation of that equipment. Robot safety, on the robot there's a kill switch that will shut down the robot in event of an electrical fire or a runaway situation. Keeping appropriate distance from the robot is also important, where all personnel will be at least 10 feet from the robot while in use.
So our performance goals for the robot this year, our robot must fit into a 1.5 by 75 meter mining area, and it must be able to traverse over this area, must be able to collect the regolith at 40 centimeter depth, and our design of the robot must be reliable, durable, maintainable, and in the spirit of space readiness. We wanted our project to be as close to a true NASA project as possible. In operation of the robot must be operated with minimum physical human contact due to, in a real space operation, humans would not be able to interact with the robot if it was on Mars and such. The robot must be able to collect, and also not just collect, but store the material and get it back into the designated collection bin in an efficient manner.
Jantown Shorter here. Our design philosophy for this project was to just move large amounts of material back and forth from the collection site to the dumping area for this project. We aim for more of an industrial type system of designing the robot itself and making improvements on a continuous improvement or Six Sigma basis. Our excavation and material systems they did well last year, but we thought we could always, like I said again, continuously improve and make improvements on the robot to ensure that we get the best product this year for the competition. And we also wanted to design and make sure the fabrication of the locomotion systems were for where we needed them to be for the project. Our design philosophy for continuous improvement was to complete the design and fabrication of the locomotion system while working on the improvements projects for excavation and collection in the bin systems. So last year we had a fairly decent run. We came in I think 27th place out of 50 schools that were there last year, which is awesome for our school. Last year we had a four-wheel design, only used two motors to run the rear wheels. The wheels caused an issue as the fin design caused us to dig deeper into the ground while we were trying to traverse back and forth on the plane, causing issues of digging and slipping with the wheels itself. We also weren't able to collect as much regolith as we wanted due to issues with the bin and the excavator. The bin wasn't giving us the angle we wanted to dump the regolith into the collection bin, and the excavator was dumping the material in between the bin and the excavator, leaving a lot of regolith not collected by our buckets. And we also ran into some issues where we weren't able to dig deep enough to collect as much regolith as we wanted, as we only got to about 5 or 6 inches into the ground rather than the 12 that majority of the regolith was located at. So this year we came up with our continuous improvement. We wanted to redesign a little bit of the robot and make improvements there. So we designed a new frame which made the robot a lot lighter and easier to access from the circuits part of it, and just maneuverability on the course. We used a track driving system rather than wheels, which helped us with traction over the surface, either the bumps or the divots that were given, and helped us to maneuver easily around the holes or the rocks that we placed on the competition course. We also replaced the bin with more of a U-shaped bin, which allowed us to collect more of the dust and give us the dumping angle that we needed to dump majority of the regolith into the collection bins. And we introduced more actuators to the excavator system to dig deeper into the regolith to collect as much material as we could for higher point consumption.
Oh. Okay, so why do we go with the track design? There's several advantages of a track design. First, power efficiency, the lack of slippage between the ground and the wheels, high traction and weight distribution over a larger area, flexibility, moving around objects, and a smoother ride to protect the electronics. The size of the hull is 33 inches by 17 inches by 4 inches, made of aluminum and plastic. The joints are sealed at every point, and the rubber track is made of reinforced Kevlar, and the keyways in the sprockets or the drive wheels are machined into it so that the center guides will go into the center piece right here, fit perfectly, and it'll keep the track from coming off. Also, it'll keep the traction within the sprocket. The driving gears, we have 4 driving motors on this mining robot. The specifications are 24 volt DC. Gear ratio is 1 to 26 to 1. The rated torque is 23 kilograms of force per centimeter. The rated speed is 136 RPM, and the final drive to the wheels is 44 inch-pounds. The front drive wheels are mounted in adjustable brackets right here that we can adjust from the very front in the event that the track slips off or there's any maintenance to be done. We can adjust it from the outside, so therefore we don't have to open up and get dust on the inside. Basically how it works is we have 4 motors going forward. All 4 motors will go forward, making a left turn. These motors, the left motors will stop, and the right motors will move forward and will turn, vice versa for the right. And if it's a pivot steer on its own axis, these motors will go in reverse and these motors will go forward and it will spin on its own axis.
So I'll be giving you the overview of the bin and that of the excavator. The bin is made up of aluminum sheet metal riveted together, and it weighs about 3.8 kilograms. And the volume capacity is about 1,800 cubic centimeters. And during the design stage, it was estimated that a gear motor with capacity of 210 inch-pound is needed to move a payload of about 5 kilograms. Currently, we have a gear motor with a speed of 8.3 revs per minute and a torque of 310 inch-pound on this robot. The bin supporting system is made up of 1x3 aluminum rectangular tubes with 1/8 inch wall thickness. The power transmission mechanism from the motor to the bin is by sprocket and chain configuration, which is buried or enclosed in this upright. The purpose of doing that is to prevent it from getting dust and foreign particles. Now moving on to the excavator. The excavator consists of a revolving conveyor chain lobe made up of 4-inch wide links, and it has a sprocket which is connected to the gear motor and another one which is idle. The gear motor runs at a linear speed of 6 meters per minute, and there are 8 special buckets attached to the excavator. And these special buckets were made in order for it to handle materials and also dig as well. And this was manufactured using the FDM additive manufacturing technology. Each special bucket can carry about 150 centimeter cube of material. Theoretically, the whole excavator can carry about 3,500 cubic centimeters per minute. The excavator has an actuators for its movement, and it has 2 cameras for the operator to be able to see where it is at every point in time.
So, to actually control the driving and mechanical functions, other mechanical functions of the robot. There is an embedded system in the form of a Raspberry Pi microcontroller, which is interfaced with all the sensors and it also supports network server capability in order for the user to communicate with it from the communications hub. The sensors, cameras, motor drivers, and other mechanical functions were interfaced with Raspberry Pi mostly through relay blocks. And the PC was connected to Raspberry Pi through the Raspberry Pi's APA. For this year's model, as mentioned earlier, the digging range improved with modifications to the excavation, the excavator, and the traction and the motion also improved as the traction was modified to accommodate the circumstances, to accommodate the terrain of the Mars environment. Data consumption was drastically reduced as we used an MQTT broker server, which is lightweight and would only require minimal bandwidth and minimal data to be consumed over the course of the user communications with the robot. Power was regulated by installing surge protectors and using less less complicated circuit components, such as the motor driver, which consumed quite an amount of power last year.
So now I'm going to talk about our project management, which consists of our team breakdown structure, our budget, and our risk management. So for our team breakdown, we broke our team up into 3 groups. Those 3 groups include the mechanical system, our electronic system, and our outreach. For our mechanical system, that included the team that constructed the frame, the bin, and the excavator. As for the electronics team, they're in charge of all of our sensors, our actuators, and our programming of our robot. And then for our outreach, that team was pretty much in charge of going out to elementary schools and encouraging kids to pursue subjects in STEM. This is our budget for our project. What I want to highlight is that we had a budget of $7,000, and out of that $7,000, we only spent $6,290. There's another budget continued of all of our components for our excavator parts, and from the chart, we only spent $744.
Of course, safety being important, we did a risk assessment. The overall risk assessment was low. Some of the hazards we identified were electrical fire, runaway robot. For mitigation, we identified that the overall risk assessment was medium. We mitigated the hazards with following. We added a safe emergency stop button on the robot and shut it down in the event of a runaway situation or a fire. Maintain a safe distance of at least 10 feet. Fire extinguishers available during the demonstration, and a low power design that reduced the possibility of fire.
To wrap it up, I'd like to thank Dwight D. Eisenhower Transportation Fellowship, the Aerojet Rocketdyne as our sponsor for this project, the VSU College of Engineering and Technology, as well as the Virginia State Engineering and Computer Science Department, as well as our advisors, Dr. Garabon and Dr. Chung, for helping us out massively with this project and giving us the opportunity to work on such a cool project. Also, I'd like to thank NASA for just hosting the event and allowing us to just work hard and show you what our school can bring in the form of aerospace technology. We hope you enjoyed our presentation, and hail state.